opportunity to give a short presentation results to my group here. My name is Volodya Bezghuba. I work at Python Research Development for the second year and the project as PhD.
Excuse me, could you speak loudly?
Yes.
Check
So
check if your microphone is on.
Should be better now.
Yes.
So I would like to tell you today about my study of electronic structure of topological iron-based superconductors, and also excuse me for my appearance because recently I was going by the bike down on a slopy road, and accidentally I found on the tone I found something like a gap, and probably it ended up being inverted, and I accidentally even got into it. So sorry for that. First of all, I would. No, it doesn't. Yeah. The subject of my study are iron-based superconductors. First, I will tell a few words about them and how are they related to the topology. Then I will say shortly, due to not to shorten this coffee break, I will say a few words about ARPES and about most studied by me compounds here, iron, tellurium, selenium, and life as lithium, iron, arsenic, shortened life as, and then some output shortly. So, iron-based superconductors, they were first discovered in 2008, and as you probably know, they are high-temperature superconductors with transition temperature Tc going as high as 55 Kelvin. Unfortunately, the nature of high-temperature superconductivity still remains to be unknown, and while these compounds, they might have different crystal structures, but they all share similar building blocks, which are iron-selenium layers or iron-arsenic layers. And you can see several different typical families of these compounds on the left and their calculated band structure on the right. As you can see, band structure appears to be very complicated, and you can see many bands crossing the Fermi level. And turns out that this becomes a very good playground for topology, because what is topology? In mathematics, it's the field which is concerned with the preservation of the properties of geometric body under continuous transition. So, in other words, if we can smoothly transform donut into the cup, they can be called topological equivalent. Same can be applied not only to the three-dimensional real space, but to the reciprocal space as well. And for example, we can see some toy band structures on the right. If we consider the gap in the normal insulator and compare it to the gap in topological insulator, in case of topological insulator, we get crossing of the gap, and in this gap, which is inverted gap, topological surface states emerge, and thus this material becomes topological. And this is interesting because it conducts current on the surface, but is insulator in bulk. And the third case of topological direct metal is almost the same, only that this is completely bulk material and there is no opening of the inverted gap. So a nice method to study all of these materials is ARPES. I won't go into the details here. I will just say that it gives you the allows you directly to see the electronic structure of the material, and it's based on the photoemission. Using this method, you can reconstruct the whole Billiard zone of the material. Like Andrei said, there were a lot of beam times over these durations. Over this duration while I worked here, it was even more for me, 9 beam times, and I don't even want to think how many months that were spent there during night and day shifts. I also participated in the SUMA setup. We measured a lot of different samples, but today I will talk only about iron, tellurium, selenium, and like I said before. And also in the lab currently we are working on the installation. We set up the new laser and now working on polarization the very nice thing about this new laser, it uses energy of 6 eV, which is a normal typical energy for the laser. But a very nice thing about our laser is that we can achieve resolution as high as 2 eV, which is in principle is even better than we have at 1 tube at best. So it's better than at synchrotron. This is how our lab at IFW looks like, and I will shorten this. I won't go into the details here. For those who are interested in it, please, you are welcome to come to join it online tomorrow during lab 2. In the lab, we have 2 light sources, helium lamp and laser, which I've mentioned before. And like Andrei said, we can achieve temperatures as low as 2 Kelvin. And yes, from one point of view, it's a bit of cheating because 2 Kelvin is not very stable. But we can hold it for a minute, which can be enough to get a spectrum. So it's actually a very good temperature for the laboratory. And here in the bottom right corner, you can see the example of such spectrum measured with the new laser, and it has resolution of about 2 million. Yeah, this is LiFS, and this cross is so now about PTC or iron tellurium selenium. This compound belongs to the 1,1 family, and the only difference is that some atoms of the selenium are replaced with tellurium. And you can see its crystal structure on the right and corresponding brilliant zone for it. The samples which we were measuring were grown by Psi group. Their critical temperature is around 14.5 Kelvin. And why we got interested in it, because there were several groups reporting this material to carry topological surface states. So it was very interesting to study it by ourselves to get more details. The group by P. Zhang, which they published their first paper in 2018, they report seeing this Dirac cone in their spectra. This is one polarization of the light, this is another polarization of the light, and they do their measurements with the 7 eV laser. They claim this to be a Dirac cone, and it aligns nicely with their calculations, which you can see on the right. PZ band crosses DYZ and DXY and even DXZ. So this part, it opens the inverted gap and in it topological surface states emerge. But there is a big complication to this. All calculations for this crystal structure are approximations due to the large size of the unit cell. And it turns out that it's very, very sensitive to which approximation you use. So as you can see on this slide, there are 4 different calculations. They are all for iron tellurium selenium, but they give completely different picture, completely different scenario. And indeed, in the second one and in the third one, we do get inverted gap opening, and we do expect the surface states. But these are calculations, and it's interesting what is in reality, what is in the experiment. So we performed a lot of experiments. A lot of data was accumulated, and sum up of them is this KZ map. It's KZ map because important notice, excitation energy of photons, in case of ARPES, it corresponds to KZ. So a nice feature of synchrotron is that we can measure with different photon energies, thus we can map the KZ. So here we can see several brilliant zones, and the first most visible thing here is that there is no visible band which would be in the center at any KZ. So there is no signs of topological surface states. If we do the cut, and these 3 cuts, these 3 pictures, they are second derivatives of this, but at different levels, Fermi level and slightly lower. And if we do the cut of this and look how it disperses over KZ, we see that there is one band which looks like DXZ, DYZ, and another band coming closely in around Z point, which almost touches the dxz dyz and then comes back up. So after analyzing all of the data and summing up all of the results, we came to the conclusion that there is no topological, no inverted gap here. And it is even not too hard to see how the group who were reporting seeing topological superstates could have made a raw error here there. If you look at the pictures below from A to D, these are our scenario of what is going on in Iron Zone Sweden. If you look at these pictures from A to D, you can see that bands 1, 2, and 3, while they go from gamma to Z over the brilliant zone, they almost don't change. Therefore, we need to have a very, very sensitive experiment to actually catch any differences. And that's what we managed to do, luckily. And if we analyze this, we see that there are no inverted gap because PZ doesn't cross dxz dyz. It almost crosses, and even if there was inverted gap, the size of it would be diminishable due to renormalization. Renormalization is the difference between calculated band structure and band structure the real band structure you see in the experiment. From calculations, the gap might be expected if the scenario is slightly different. If it indeed crosses it, it is expected to be several milliV, which means that in reality, the real size of the gap would be like 1 milliV or even smaller, which is not possible to see with ARPES. But still, this material is very interesting because it's strongly correlated to superconductor. We do get 2 Dirac points here and here of different types. So this is first big result. Another compound which I studied, which was grown this year, is LifeS. It was grown by Igor Morozov and Anna Vorobyova, and we managed to measure not only pure LifeS, but also doped with cobalt and with vanadium, which cobalt and vanadium in this case serve as electron doping and hole doping, essentially. And these materials are also expected to carry topological superstates. There are articles by the same group where they report seeing topological superstates and Dirac coins. In their paper, again, we start from calculations. There is again PZ band, which comes from iron, and it dives very deep, crosses all of the bands. And here, indeed, we see opening of the inverted. We expect opening of the inverted gap, but on their spectra, it looks a bit strange because it looks more like the crosses they see with high cobalt doping correspond to Dirac cones, so to topological Dirac semi-metal cones, not to the inverted gap. That's because if we see such spectra even with laser, like I shown before, it does look similar to that. Though this is not even cobalt doped material, so Fermi level is not shifted, it's just pure LifeS. And also, if we look closely at the size of the inverted gap they report in their calculations, it is expected to be on the scale of 30 milliV. And in the experiment, they see the inverted gap of the size of 25 milliV, which means no renormalization, basically. And that's also very strange because iron-based superconductors are famous to have strong renormalization, like I said before. In our scenario, there is very well known calculations from Sergei Gerasenko group from the paper in Nature Physics 2016. Here, the size of the band inverted gap is around 20 milliV, and we have also, from the past, we have a very nice KZ map, mapped from 20 to 100 TeV, very detailed. And here, unfortunately, it's not possible to see inverted gap at this side of brilliant zone. So we got interested, maybe we can see it if we go lower in the energy, to look at it in more details, to map it from 20 eV and below, as low as possible. So we did that over our last due time. This is the result, but very rough. So let's put it closely to the map on the right. And here you can see that it complements the easy map indeed very good, but still there is no clear sign. It is not possible to see inverted gap here. First of all, it should be very small. Like I said, we expect it to be, from our calculations, we expect it to be on the size of 20 millieV. So with renormalization, it gives us like 6 millieV. And secondly, it looks like bulk bands GXZ, DYZ, and PZ are so strong that they just crush everything, and you can't see anything here over the intensity. So there is inverted gap here, but it's not possible to see it. The same was done for vanadium sample doped with holes. So we get, in this case, you might notice that Fermi levels don't correspond. It's because it's electron doping, like I said before, so it should be shifted up. With vanadium, we get it shifted down. This is the detailed zoomed in picture of the map we complement to this old map. And this is the overall picture in which, again, we see signs of something going on, but we don't see inverted gap itself. It's not possible to map it, unfortunately. It looks like, to sum up this part, it looks like in their article, the parts they report to be topological surface states is actually, like I showed on this slide, it's actually the Dirac cone from the crossing this pattern event. And the higher one, which is topological Dirac metal cone, it comes from crossing this gamma. So detailed study of iron, tellurium, and selenium revealed that it's 3D Dirac, that it does carry 3D Dirac points, but there are no topological surface states there. For LifeS, we managed to get low photon energies map, and it is not visible on inverted gap is not visible on it due to the gap being too small and due to the too high intensity, too strong bulk bands. Also, a new laser was set up. A lot of other things were done in the process, like the SUMA test and other, but let's not focus on this for now. And my further plans are the continuation of the study of lithium iron arsenic with other types of doping, with higher doping of cobalt maybe, also 7 EV and 11 EV study of these compounds as well, both iron, tellurium, selenium too, because we want to have, we have spectra which look exactly like the one in the paper by Zhang, but it would be nice to have exactly the same energies, which is definitely the same people. And to measure the sample, other samples drawn by Volodya and Hans. And lastly, I would like to thank everyone who was helping me in this long, on this long journey. My supervisor, Sergei Borisenko, Professor Dr. Buchner, who is one of the initiators, also Professor Dr. Kurdyuk, who is my supervisor in Ukraine, who is also one of the people responsible for UKRATOP projects. Everyone who is responsible for UKRATOP projects, all sample growers, my colleagues, technicians, staff at Synchrotron, without whom it would not be possible to do this. Alexandra Reiska for calculations, of course, because without this is the first motivational step from which we become. And you, of course, for your attention. Thank you.
Thank you, Volodya. The session is open for questions. Then,
so I have a question on this vanadium doping. Mm-hmm. How large is this shift? Is it that do you really see, let's say, a rigid shift in place of the polio?
Please repeat the question because yes, the audience cannot hear it.
So the question was about how much vanadium doping shifts the Fermi level. It does shift it. This is still being prepared for the publication, so it's rough picture just for the presentation, but it's about 10, 15 milli-electron volts shifting, and this is even with low saturation of vanadium in the compound.
And that also means that really the battery is discussed a lot about the band structure, so we come up on the whole bands, but they really, let's say, disappear at the front surface really changes the front of the doping.
Unfortunately, I don't. Well, I don't have them in the presentation. I have only the Fermi map for the cobalt doping.
Yeah.
But with vanadium doping, it looks it has some changes, but they are very minor, and it's more noticeable on the map when you do all the renormalization, not renormalization, all the normalization of the spectra, so that it looks nicely, and then it's noticeable that here intensities are lower than in this case. But this I think it's just normalization effect, and the changes of the Fermi level, Fermi level changes, but slightly. Yeah.
Hopefully be sharper, and then one has a chance either to see the surface layers or see them in transfer. And this is what, because the guys who did this before, they saw, as we now understand, two bulk derived points. And the topological was smeared out by the spectrum. So those two processes which they saw were two, the upper one they never showed, because it's there. And the topological one has to be first brought to the Fermi level in order to be sharp and maybe go into transfer. So more vanadium controlled buildings would be right. Yeah.
And indeed, if you look closely on this detailed map, it looks logical that if we shift it slightly higher, inverted gap looks like it should be somewhere here, because if we map Z like this, it's expected to be somewhere here, so if we shift it from the level, it might look better.
This is the Z direction, that's why everything is there.
I know.
You see the perpendicular spectrum, then you clearly see all this crossing. And I see no reason why the surface topological spectrum should not be visible when we approach it. Then there should be sharp and visible. The more vanadium will control it.
Very interesting then to study the transport also.
Yes, and that was the transport.
Okay, do we have questions from the faraway audience?
I may ask. Can you hear me?
Go ahead, Sasha.
Yeah, can you hear me? About FST. The question: have you you said that you observe Diracons, but not at Z point, right?
Yes. Should I repeat the question? Yes, we see it. We expect it to be one of them closer to gamma, another somewhere between gamma and Z.
So, but this corresponds to this crossing which you see in calculations.
Above the Fermi level.
And this is the crossings of the bulk states. It's not surface states.
No, they are bulk.
Okay.
This is the crossings of the bulk states.
Okay, thanks.
So,
Can I just continue that? So yeah, there is a Dirac crossing, 3D Dirac crossing.
Mm-hmm.
If there is a superconducting state, do you see that there is could you see that there is a gap opening up on the 3D Dirac? Could that be something to be able to resolve?
We do see the gap. Not in the Dirac point, but in general, we do see the opening very nicely. But in case of the gap, I didn't look closely at it. It's not at the same level. It's not at Fermi level. So
yes, this one is quite deep. It's 20 eV, the one which type 2 Dirac.
it shouldn't affect it.
Bring it to the current level.
If we bring it
Again,
in
slower than that. And if one goes more to Urim, then probably this easy band will dive deeper, will cross the lower one from the USC, will open the inverted gap, and there will be such a state, but the gap is tiny. Again, it's really fine tuning to bring it to the current level, very tiny gap. So,
I don't know if you're on the way, right? Well, you could say, I want to open the gap at the neutrality point, and even the upper, the type 1 is above the kernel level.
yeah,
Yes, this is above.
Yeah, it's pretty sure it's there. So if one goes up, then it will, yeah.
But even now, you could, okay, you need to go still. But it depends on the energy state.
Always high temperatures actually. How much is it? I think it's 75, 70, even numbers. How much about the kernel level is. So maybe at higher temperatures, you actually populate this. And these here are points of type 1 is actually populated at higher temperatures. So
We did measurements only with low energy, with low temperatures. This map, for example, it's, if I remember correctly, it's around 1 Kelvin at measured at 1 cube. We also have data with 20 Kelvin, so that we are above TC, but there is no like high temperature data. The highest we have is 20. So yeah, indeed, maybe, but I think it should be not lower than 10 millieV until that direct crossing. So I'm not sure that temperature will give us enough resolution if we reach.
And the crossing is that down?
The crossing of the expected inverted gap.
Not the direct one, so the direct crossing, the point B. That doesn't look like to be a gamma.
No, it's between gamma and Z.
It's between gamma and.
Oh,
yeah, it's on the Z line.
Yes.
Okay.
Yeah, I mean, it's on this vertical line, but
it doesn't need to be on the high synergy point in the third.
Yeah.
Maybe a general question. Actually, I see that's interesting to follow all these stories, but is there any, let's say, from vision point of view, or maybe a theory point of view, is there any estimate of other, let's say, quantities which is really affected by these? Because this iron, selenium, selenium are very good metals. And I do not expect to see anything in the transport if there's some kind of sort of safe hard to imagine that you will see any consequence, let's say, in the stupid macroscopic properties. Is there anything which we can explore then if we manage to fine tune the things? Is there any prediction on that or any let's say,
certainly that you will not do ARPES. But you could say if I can tune this.
Then we have, but what do we have to do to prove that they are marijuana?
Voltages.
So we have to do SDM. At the end of the day, we're preparing SDM experiments which don't include in terms of marijuana. Is this a correct statement?
Yeah. All these experiments which came out in these papers, they're fine, but they are not fine in the sense that this material is still not suitable. If you find a material where this inverted tiny gap is at the level, then all these stories come back and one has to measure the right material.
But these stories are SDM.
Mostly, yeah, as far as I know, they're mostly SDM.
So the superconducting state is an interesting state in any case. And in STM, there would be this firm, Majorana firm, is related to the core of the superconducting vortex. And one way of looking at it would be simply to straightforward look at STM. But there are also these things that Claudio predicted and we are working on, which are much more fancy. So there are new, say, transport effects allowed in the superconducting state.
And the other one superconducting state is also interesting.
Yeah, it's very interesting.
Interface is probably no, but superconducting state,
Yeah.
because the superconducting state is already
Yeah.
dead because there's no voltage to measure. So you have to go to some kind of interfaces, some kind of complicated structures.
But still before that, we need to find the correct compound so that we can, and that must be done probably with ARPES.
That's out of question. That's out of question that the first step is to do, let's say, do the experiments on the right material, to do the optimization of the electron structure, and that's fine. But then you can also ask, so if you manage to do that, what can we do as a next step? And this is also not trivial, let's call it like that. You cannot simply do a split measurement and see something.